Hi guys, I Aziz welcome you to CoedMaster, and in this video I am going to talk about tree data structure. I will explain what is tree data structure, why we need tree data structure, what are the terminologies that we use in context to tree data structure, and what is the time complexity of most commonly used operation that we perform on tree data structure. So make sure to watch this video till the end. So let's get started. Alright guys, let's begin this video. So guys, if you look at this collection hierarchy diagram, you will see that there are three general purpose classes that implement set interface. One is hash set, second one is linked hash set, and third one is tree set. So guys, these two classes, hash set and linked hash set, is an implementation of hashing. Okay, this means these classes internally use hashing to implement hash set and linked hash set. And the tree set class internally uses self-balance binary search tree. And if you look at the map interface, there are three classes: hash map, linked hash map, and tree map that implements map interface. And out of these three classes, hash map and linked hash map is implementation of hashing, and tree map is implemented using self-balancing binary tree, that is a red-black tree. So my friend, in order to understand all the general purpose classes that implement set and map interface, it is really crucial to understand what is hashing and what is tree. So in this video, I am going to give a brief introduction of tree, and in next video, I am going to give a brief introduction of hashing. So my friend, it becomes very easy for you to understand these classes that internally uses hashing or tree. So let's begin with the first question, that is, what is tree data structure? So guys, tree data structure is a non-linear hierarchical form of data structure in which data is stored and organized in a hierarchical structure. So in previous videos, we have seen the arrays and linked list and how data is organized in array in linear fashion, and similarly data is organized in linked list in a linear fashion. Now conversely, in tree data structure, data is organized in a hierarchical structure like this. So we have 10, then we have 20 and 30 below 10, and then we have 40 and 5 below 20. But tree also uses the same concept that is used in linked list. So in linked list we have node and all the nodes are linked to each other. Similarly in tree also we have node and this node are linked to other nodes that are 20 and 30. So guys, whenever our data is arranged or organized in a hierarchical structure, we call it tree. As simple as that. Now this brings us to the next question, that why we even need tree data structure. So let's try to answer this question with this real world example. So let's say we have a folder structure and we want to represent this folder structure. Then how are we going to represent this folder structure? Obviously we need some sort of data structure that is used to represent this folder structure, right? So this is where tree data structure comes into picture. So you can see over here is the folder structure is represented using tree data structure. So we have desktop on the root, then we have 4 folders, and inside of this folder we have another child folders, okay? And we have also some files. So this is how we are leveraging tree data structure to represent folder structure. The next example is, let's say we have so many classes and all of these classes are inherited to some classes. So let's say we have person class, and student and employee class inherits from person class. Then we have math student, CSS student that inherits from student class. Then we have professor and staff class that inherits employee class, so on and so forth. So when we want to represent this type of hierarchy in object-oriented programming or in context to inheritance, we can use tree data structure. And using tree data structure, it becomes very easy to represent this type of structure. So these are just a few 2 examples that uses tree structure to represent the data. There are numerous applications of tree data structure as well. So I hope now you understood very clearly that what is tree data structure and why we need tree data structure. Now let's move on and see some of the terminologies that are used in context to tree data structure. So let's say we have this tree data structure and these are the terminologies. So the first terminology of tree is node. So similar to linked list that all the nodes are linked with each other, in tree also we have node that are linked to each other. So here you can see that there is one node and the value of this node is 10, and this node is linked with other 2 nodes and the value of that nodes is 20 and 30. So as in linked list, node contains 3 fields. One is data and the other 2 are the pointers to left and right. Similarly, in tree also our node contains 3 fields. The first field has data and the other 2 fields has address to its child node. Okay. The next terminology is the root. So the topmost node of the tree is called root. So the next terminology is child node. So the node that is immediately below of any specific node is called child node. For example, the child of node 10 are 20 and 30. Similarly, the child of node 20 is 40 and 5. So the next terminology is parent node. So the immediate node that is above any specific node is called parent node. So in case of 40 and 5, the immediate node that is above 40 and 5 is 20. So 20 is the parent of 40 and 5. Now the next terminology is subtree. So friends, tree is recursively in nature by default. So what does it mean? So the properties that is true for the entire tree is also true for the subtrees. And what is the subtree? Subtree is a smaller part of a tree. So for example, this is an entire tree and the subtree of this tree is this much. So 20, 45 is a subtree of this entire tree, and 38, 30 and 80 is again a subtree of the entire tree. So that is why it is recursive in nature. So the properties that is true for the entire tree is also true for the smaller version of the tree. So the smaller subtree also has node, root, child, parent and so on and so forth. Now the next terminology is descendant. So all the nodes that are below any specific node are all descendant nodes. So in case of 10, all the nodes that are 20, 30, 45, 8, 30, 80 are all descendants of this node. Moving on to next terminology, that is an ancestor. So all the nodes that are above a specific node are called ancestors of that node. So in case of 20, the ancestor is 10. In case of 30, ancestor is 10. In case of 8, 30 and 80, the ancestors are 10 and 30. Because 10 and 30 both are above these nodes. Now the next terminology is degree. So degree defines the number of nodes that are attached to any specific node. So for example, in case of 30, there are 3 nodes that are linked to 30. So we can say that the degree of 30 is 3. Now the next terminology is leaf node. So the leaf node are the nodes that has 0 degree. Okay, because there are no child nodes of these nodes. So we can say that these are the leaf node. Now the last terminology is internal nodes. So all the nodes that has non-zero degree are all internal nodes. So we can say that 10, 20, 30 are internal nodes. Why? Because the degree of 10 is 2, degree of 20 is also 2 and degree of 30 is 3. That is why these are internal nodes. So guys, these are all the terminologies that we use most often when we talk about tree data structure. Now let's move on and understand what does it mean by binary tree data structure. So a tree is said to be a binary tree data structure if it follows the properties of binary tree data structure. And what is the property of binary tree data structure? That every node has at most 2 child nodes. So the property says that every node has at most 2 child nodes. So if you look at this structure, every node has at most 2 child. So 10 has 2 child, 15 and 20. 15 has 2 child, 5 and 1. And 20 has only 1 child. If child node is less than 2, that's okay, but it should not be greater than 2. So any tree that follow this property becomes binary tree. So guys, I hope now you understood binary tree really well. So now let's move on and understand what is binary search tree. So a binary search tree, a tree in which for every node, all the nodes on the left subtree is smaller and all the nodes in right subtree is greater. If this property is followed, then we can say that it is a binary search tree. Okay, and in binary search tree, all the keys are typically considered as distinct. So we should always be having distinct key in binary search tree. So let's see this structure. In this structure, you will see that the root node is 20 and all the nodes on the left of 20 are smaller than 20. 15, 12 and 18 are smaller than 20. And if you look at the right subtree, you will see that all the nodes are greater than 20. 30, 25, 40, 35, 50, all nodes are greater than 20. So that is why this tree is a binary search tree. Now you might have a question that what is the advantage we get when we impose these strict properties on this tree? So well, the advantage of imposing this property lies in the in-order traversal of binary search tree. What is meant by in-order traversal of binary search tree? It is just a way how we traverse all the nodes of the binary search tree. So in-order traversal, we are going to first traverse the left subtree, then root and then right subtree. So let's traverse this binary search tree using this specification. So let's start traversing this tree from first node, that is the root node. So let's start with the 20. So in-order traversal says first go to left subtree, then go to root and then go to right subtree. So 20 has left subtree and right subtree. Okay, so let's go to left subtree. So left subtree has 15, 12 and 18. Now again, as the recursive nature of tree, again we have to go to left subtree, and the left subtree of 15 is 12. Now 12 has only one node, so we print 12 on the screen. Then as per the in-order traversal, after traversing left subtree, we have to go to root. So the root of 12 is 15. So we print 15 on the screen. Then after root, we have to go to right subtree. So right subtree of 15 is 18. So 18 gets printed on the screen. Okay. So we are done with 12, 15 and 20. Now left subtree is complete. Now let's go to root. So the root is 20. So 20 gets printed on the screen. Now after the root, we have to go to right subtree. So when we go to right subtree, we get this right subtree, and the root node of this right subtree is 30. Now again we have to follow the same pattern. Let's go to left subtree of 30. We have 25. So 25 is printed on the screen. Then go to root. So 30 gets printed on the screen. Then go to right subtree, that is 40. And this 40 has again left and right subtree. So let's go to left subtree, 35 gets printed on the screen. Then print root value. So root value is 40. And then print the value of right subtree. And the right subtree has only one node. So that's why 50 gets printed on the screen. So this is how when we perform the in-order traversal of any binary search tree, all the elements are taken out in an ascending order. So because of this property of binary search tree, many data structure like tree map and tree set uses binary search tree data structure as an underlying data structure to implement itself. So I hope now you understood what is binary search tree. Now let's see the time complexity of most commonly used operation that we perform on binary search tree. So let's say we have a binary search tree here, okay? And the three most commonly used operations are search, insert and delete. So let's say we want to search 40, okay? So we start from the 20, that is the root node, and then we decide whether to go on the left side or whether to go on the right side, because all the elements that are in the left subtree are smaller than 20 and all the nodes that are on the right subtree are greater than 20. So as we want to search for 40, we can simply skip the half of this subtree that are less than 20, and then we can move to the right of the 20. In right we have this subtree. Again 40 is greater than 30, so we can again skip the half of the tree and move to the right of the 30. And after moving right to the 30, we get the desired number. So we can say that while searching any number in binary search tree, in every traversal we are simply ignoring half of the tree. So we are dividing the number of nodes into half. So whenever we have such scenario where we divide number of nodes into half, then it always give logarithm time complexity. So we can say that in searching operation, the time complexity of searching any number or any element is big of log of n. Similarly, if you want to insert any element, that let's say we want to insert an element 55. So what we do, we start from the 20, then we skip the entire half of the tree, okay? Then we go to 30, then we go to 40 and then we go to 50. And then we insert an element after 50 because 55 is greater than 50. So you can see that we are skipping the half tree here, then again we are skipping the half tree here, then again we are skipping the half tree here. So in every iteration we are skipping the half tree. So we can say that insert operation also takes big of log n time complexity to insert an element. Similarly, if you want to delete an element, let's say I want to delete 50 from this tree. So what do? We start from 20, we skip half of the tree, then again half of the tree and again half of the tree. Then we reach 50 and then we can delete 50 safely. So guys, do you realize what is happening over here? We are simply following the binary search algorithm. And what do we do in binary search algorithm? In binary search algorithm, we divide the input by 2 again and again and again. Okay? That is why the time complexity comes out to be logarithm. So here, the time complexity of all these operations are big of log of n, where n is the number of nodes in the tree. So guys, I hope that now you have good understanding of tree data structure, that what is tree data structure, why we need tree data structure, what are the terminologies that we use in context of tree data structure, and what are the time complexity of most commonly used operation on tree data structure. Now in next video, I am going to give a brief introduction on hashing. So after studying hashing, we will continue our learning with the map interface of the Java collections framework. So guys, this is all from my side. If you have learned something valuable from this video, then hit the like button in order to make YouTube algorithm happy. Please subscribe to the channel and don't forget to click the bell icon so my friend you never miss any upcoming videos. Thanks for watching. See you in the next one.